was launched at a side event of the UN Statistical Commission on the 9th of February 2023. The purpose of using privacy-enhancing technologies, also known as PETs, is to make the sharing of sensitive data between various parties possible. The focus of the guide is then also on the question, how can we use technology to mitigate privacy risks and give provable privacy guarantees throughout the collection, processing, analysis, and distribution lifecycle of potentially sensitive data? Protecting data from unauthorized access, processing, or distribution is the simple goal of PETs. The drafting of the guide was a collaborative process with many experts contributing from the statistical community, but also from the private sector, academia, and civil society. They all see the societal benefits of improved and safe sharing of relevant microdata for better public policies. I'm Jess Stahl, Vice President for Data Science and Analytics with the Northwest Commission on Colleges and Universities, and I'm also a member of the UN Task Team on Privacy Enhancing Technologies of the United Nations Committee of Experts on Big Data and Data Science for Official Statistics, a member of the UN Pet Lab and Open Mind. I'll be moderating the open house today. There will be time reserved for questions after the speakers have concluded, so we ask that you write any questions or comments in the chat throughout the presentations, and we'll respond to as many of those as possible at that time. Also, this open house is being recorded, and the recording will be available on our website after the event. We will place a link to the website in the chat. And now I'm very pleased to introduce Mr. Mathias Jog, Chair of the UN PETS Task Team and Head of CIO Office Statistics Netherlands, to provide some opening remarks.
Yeah, thank you, Jess, for this nice introduction. And yeah, first of all, I would like to welcome all participants to this webinar, and also particularly the speakers who agreed to spend their time to present. And this is on behalf of both UN, United Nations, as well as international community of official statistics. So as an introduction, I would just like to say a little bit about the importance of privacy for official statistics. So why we have this task team that Jess mentioned, and why we are doing these webinars. So the statistical offices are providing very important statistics to societies, and they have been doing this for many years using surveys, using censuses, and using data from government registers. However, in this time of change, and you have experienced this time of change yourselves, for example, pandemic, the energy crisis, the war, the food security crisis, governments need really timely and trusted data. And the national statistical organizations are positioned to provide this data, but we need to look into the new data sources, including the data sources, the data that is privately held, for example. And this is where privacy protection and data protection in general becomes really, really important. So Jess already mentioned that we published UN PET guide, which is helping statistical organizations to understand the technologies that are currently evolving to protect the privacy, but also other aspects such as what are the types of use cases that we are using it in, what are the legal aspects, what are the organizational aspects. And I often hear in these discussions that the technology is the easiest part. So all other aspects could be very tricky, like the skills, for example. But we also need the place where we discuss technology and methodology. And the reason is that the things are evolving very fast, which we also observed while working on this guide. And that's why I really welcome and look forward for the discussion today will be exclusively on the methodology of privacy enhancing technologies. So more technical discussion that we need to have to understand where the technologies are and how mature and how usable they are for the use in official statistics. So by that, I look forward for the discussion, and Jess, giving back to you.
Thank you so much for those opening remarks. And now please welcome Mr. Robert Pisarcek, co-founder of Oblivious AI, who will provide an introduction to the rationale and overview of Chapter 2 of the UN Pet Guide.
Thank you, Jess. So maybe let me share my screen. I'll have a few slides. Sorry, can you see my screen? I hope yes.
Yes, perfectly.
Okay, perfect. Okay, so before each speaker dives into specific technologies, I basically wanted to say a few words about the chapter in general, what it's about, and kind of its rationale, as Jess mentioned. So the purpose really of that chapter is to provide specific kind of introduction to 7 privacy-enhancing technologies in particular, right? And the way it's written mainly for practitioners or data practitioners from national statistics offices. So it really has kind of NSO in mind. But of course, we hope that it can find its use even beyond NSOs. And to be honest, we've already seen other public and private institutions using it as a reference guide. But one could have kind of the core aim of this chapter is to present different paths, privacy-enhancing technologies, in a consistent manner, such that it can act as a kind of easy reference and comparison on different paths. It also, towards the end, include a longer section on practical considerations when deploying pets in real-life scenarios. So there's kind of one thing is about the theory, but another thing is like how do we actually practically use them, especially in the kind of the NSO context. So how do we choose appropriate technology? What considerations to take when we actually involve multiple actors, data owner, infrastructure owners, etc. So of course, this chapter is a product of work of multiple people from NSOs, academia, industry. So there's 7 editorial board members, 11 contributors, additional external experts. So I wanted to say huge thanks to all of them. But one thing to stress is that it also builds upon the previous version of the pet guide. And so we very much see it as a kind of living organism. Hence, any feedback, even after this call, is very welcome. So what is the approach taken in the handbook when talking about pets? Well, firstly, we always start with a problem definition, right? So even though we put all those different pets on a kind of single term, they actually often solve very different aspects of what we might call data privacy. So some of them can be used interchangeably in certain contexts, like trusted execution environments and secure multi-party computation, while some can be combined, like Enclaves and differential privacy. So within the chapter, we also offer example use cases, mainly with NSOs in mind again. There's also, of course, a separate chapter fully devoted to use cases. Here again, an ask is that if people are aware of any use cases that use pets and would like to share them, please also do reach out. We're also working on a use case depository, which will be regularly updated. Furthermore, there's also in the chapter an overview, of course, history and background sections, which also include references to open source libraries. So again, any information about those is useful. However, importantly, kind of the 2 major sections in each kind of description of the technologies are around security models and cost of using those technologies. So they're again written from the perspective of data practitioners who are not necessarily cryptographers or security experts. Okay, so what are actually pets, right? So privacy tag is a very generic term that can mean, most from kind of technologies that help you with filling in privacy policies or helping tracking data as it moves through organizations. Here, what we care about is actually pets that specifically help with the following, right? So firstly, they allow to combine data from siloed data sources. So this can be even from different organizations that want to collaborate without exposing sensitive information to each other, as actually Matthias mentioned. But secondly, pets can also provide guarantees that data is only used for a specific pre-approved application and not outside of the scope of its intended purpose. So in this way, it kind of act as a technological addition to the typical legal guarantees. And finally, pets can also be useful when sharing and disseminating data by, of course, offering tools to prevent reverse engineering of sensitive inputs from the aggregate statistics that is being more widely shared, which is again, of course, a huge task of national statistics offices. So the guide kind of often refers to particular categorization of some paths. So let me maybe mention it now. So in a typical data processing context, we can break any process into kind of three straightforward distinct parts. So there's of course the inputs, there's a function or computation that acts on that data, and there's of course outputs of that computation. Now, different paths help to protect different parts of that data flow. And kind of most of them can be kind of broadly categorized into either input privacy or output privacy. So input privacy is about how to protect the input data while it's being processed. So an example are, again, those two or more parties that wish to run analytics without directly sharing data with each other. Output privacy is very much about kind of limiting what can be learned from the about the inputs from output of the computation. And the guide discusses 7 paths in detail. And in the following presentations, the speakers will dive into kind of specifics of 4 of them. So for example, secure multi-party computation and homomorphic encryption can be viewed as input privacy techniques that allow to perform computation directly on encrypted data. While, for example, trusted execution environments are also input privacy technique, but they base their security on hardware assumptions. So like very different security assumptions here. On the other hand, differential privacy is an output privacy technique that basically complements typical statistical disclosure controls. There are also 3 technologies that are in the chapter, but will not be discussed in this session. But of course, I highly encourage everyone to read through those. And these are synthetic data, which are essentially about creating fake data that resembles real data under certain characteristics or correlations and so on. The synthetic data can also be differentially private. There's also distributed learning, which is about training neural networks on input data that is owned by multiple parties who want to keep these data private. And the guide also discusses zero knowledge proofs as well. So as I mentioned, one aspect discussed in the chapter that is always worth sort of bearing in mind are practical considerations. So there are a lot of paths and there is no single path that solves all of the problems. So for each applications, different choices needs to be made depending on specific circumstances, from the size of the computation, type of the computation involved, infrastructure, fairness consideration, etc., etc. So I also believe that Owen will talk about this shortly as well. So with that, thank you, and I will now pass on to the next speaker. Thank you.
Thank you so much. At this point, we'll hear from 3 experts who will discuss several specific methodologies utilized for input privacy. We'll hear from Dave Archer from Galois Inc., who will discuss secure multi-party computation, Kay Han with Samsung, who will discuss homomorphic encryption, and Robert Pisarczyk from Oblivious AI, who will be discussing trusted execution environments.
Hi, this is Kay Han. So I wonder that the David Archer is presenting, or I heard that I should present about MPT topic also.
Yeah, Dave Archer won't be able to make it today, so you can take care of the 2 sections.
Yeah.
Thank you.
Okay. So this is Kay Han. So I will try to share my slide, but I don't know why, but my web browser version of this Microsoft Teams does not work. So I'm trying to use my phone. So I hope this works. So let me start my presentation. So I'll first briefly introduce about this secure multi-party computation, and next go to the homomorphic encryption. So okay. So maybe I just use the drag. So just introduction is like, first, the secure multi-party computation is about the input privacy. So secure multi-party computation, for short SMC, supports the computation for inputs from different parties without revealing each party's input. So in this figure, you can see that each party has the input xi, and they want to compute some kind of function fx without revealing each party's input. And actually, the performance of this SMC depends on the number of parties, or what kind of computation you want to compute, and what kind of setting your security. For example, the semi-honest model assumes that each party will follow the protocol, but in case of the malicious security setting, each party does not follow the whole protocol. They will try to fake the other parties to like using some fake inputs. So this is introduction. So I think in the document, in the guide document, there are introduction of these two kind of techniques, which is called the goblet circuit and linear secret sharing. So I just want to briefly introduce these two techniques. I want to give the audience to the insight of what kind of technique is. So first, in case of the goblet circuit, you can see the figure. I'm not sure how big you can see this. So in this figure, you can see that there's multiple kinds of encryptions. Like for each gate, there are 4 kinds of encryptions. And actually, here in the figure, the encrypt C0, D0, F1 means that F1 is encrypted using the key, the C0 and D0. So suppose there's 2 parties. So one party is evaluator, and second party is generator. In here, actually the party 1 is has the input corresponding to the first and third input of this gate. I mean this circuit. So in this circuit, there's 4 kinds of inputs, like corresponding to A0, A1 to the D0, D1. So first, the party 2 will generate this kind of figures, like encrypt using some random wires or something, and party 2 will send this encrypted data and B1 and D0, which is corresponding to his input. And after that, the party 2 will send to the A0 and C0 using some technique which is called obelisk transfer. So after that, like because the evaluator, the party 1 has all the red marked one, like A0, B1, C1, and D0. So using those encrypted data, they can recursively get this E1, F1, after that get G1, G0, and after that get H0 and I1. So during this evaluating process, there is no information about the inputs actually. So after returning, after the evaluator returned this H0 and H1 to the party 2, and as party 2 knows that H1 is corresponding to the 0 and I1 is corresponding to the 1. So he knows that, okay, this output of this circuit is 0 and 1. So this is a brief concept of what the goblet circuit is. And in case of the linear secret sharing, it's much more simpler than the goblet circuit, I think. So party 1 has the input 100, and this party 1 will split this 100 by 4, like 10, 20, 50, and 20. So summation of these 4 value will be the real inputs. And give this 10 to party 2, 20 to the party 3, and 50 to the party 4. So each party has this linear secret shared value of this 100. And with the help of some techniques, which is called the Beaver's triplet or something, the various computation can be done in this status, which means that they don't need to recover this value. They can compute addition and multiplication in secret shared status. So using these 2 kinds of technique, the various kinds of computation can be done without revealing their inputs. So there are there's many example use cases for the SMC actually. So first 1 is also included in the UN PET guidebook. So first one is about sharing the sensitive data among the data agencies. So NPSAS, which is short for the National Post-Secondary Student Aid Study, and the other party is the National Student Loan Data System. So in the United States, they use the SMC to collaborate to compute average loan and granted value for 30 student categories. So for more information, please see the case study 18. And Also, there's another example use case, which is called the joint statistical between the financial institute. So Italian National Institute of Statistics and the Bank of Italy did some privacy preserving record linkage and using their common key, which was a text code in their use case, and they try to compute the various statistical computations corresponding to their common data sets. So also, for more detailed information, please see the case 35. And actually, I just want to mention that there's many use cases, but I think that most of the use cases are about these common data sets. So private set intersection is quite important technique in the SMC. So there are many examples such as password monitoring, which is to alert the users that your password is breached or not. So in Edge and Chrome, there's a password monitoring service, and actually, client does not want to send their password to the server. So for this purpose, the private set intersection is used actually. And also there's a system which is called Apple PSI system. So in this Apple PSI system, this PSI is used to detect this child sexual abuse material things. So these detections makes this kind of materials to upload it in the iCloud or something. And also there is another example that which is called the private ID or private matching. So the Facebook Meta, it has some kind of public GitHub repository corresponding to this technology. And our company, the Samsung SDS, also did some proof of concept for this kind of use case. So please see the case 37. And actually the history of the SMPC is quite long. Like it started with the Yao's millionaire problem at 1982. So this Yao's millionaire problem is about which of them is richer without revealing their actual wealth. So beginning with this 1980s, there's various kind of techniques which is called obelisk transfer and gobble circuit and joint double protocols and extra. And very recently, by the requirements from the public and private sectors about this secure multi-party computation, so MPC Alliance is started since 2020, and also there are various open source software libraries help people to use MPC technology in real applications. So there are some examples, and there are many more open source libraries are there. So please try to find it. And the last thing about the SMC is what is the cost of using SMC? So first, trivially, there is some computational performance or some computational cost and communication cost. So actually, I will introduce some things about the homomorphic encryption in the next slide, but computation performance is much better than the homomorphic encryption in case of the SMC. But the communication cost is quite large. So this is some example number. So in some previous work, they tried to run this secure the machine learning inference of the ResNet 50 model in two-party computation setting. It only takes about 30 seconds. So I think it's quite fast, but it requires almost 7 gigabytes communication was required. And another maybe cost or some problem of using SMC is the floating point operation is quite expensive, but thankfully the fixed point operation is supported now. So maybe some real application can use the SMC still. And the another problem is this is not mentioned in the guidebook actually. So network connection is one of the costs of using SMC. So during this secure computation, all the parties should be connected in network. But actually, in case of the Korea, there's some kind of regulation about this sensitive personal information. So all the sensitive personal information should be saved in their own private network. So this means that two kinds of this sensitive information from two different organizations is hard to connect directly using some public network. So this is a brief introduction about the SMC. Maybe I I will move to the homomorphic encryption. So I should take some question at this point, or I can keep going on about the next topic.
You can continue on and we'll answer questions a bit later in the program.
Okay, thanks. So let's move to the homomorphic encryption. So it's still me. So let's do some introduction. So homomorphic encryption is encryption scheme that supports operations between the encrypted data. So in this figure, each data is encrypted and it becomes the input of some functions. And this evaluation can be done in encrypted state. And after the evaluation, the decrypted result will be same with some plain text result. So performance of homomorphic encryption is highly depends on the depth of circuit or what kind of computation we are willing to do. So before go into some details about the homomorphic encryption, I want to clarify the classification of homomorphic encryption. The first one is the partial homomorphic encryption. So partial homomorphic encryption means that they only supports one of the operations. So additive homomorphic encryption only supports addition between the encrypted data, and multiplicative homomorphic encryption only supports the multiplication between encrypted data. And next class is somewhat homomorphic encryption, which is also called the level homomorphic encryption. So in this case, both addition and multiplication is supported, but only the limited number of them is supported. So, for example, the BGP or BFA, CKK schemes are kinds of somewhat homomorphic encryption. And lastly, there's a fully homomorphic encryption. In case of the fully homomorphic encryption, both addition and multiplication is supported, and the unlimited number of them is supported. So this is thanks to the functionality which is called the bootstrapping. So by combining the bootstrapping with somewhat homomorphic encryption, we can construct the fully homomorphic encryption, and this idea was originally proposed by the Gentry at 29. So also in case of the homomorphic encryption, there are various kinds of use case. First one is electronic voting. So in case of electronic voting, they use the additive homomorphic encryption. And there are another example about the collaborative analytics. So in case of the Korea, there was a big scale the collaborative analytics between the Korea Credit Bureau and the National Pension Service. They want to analyze about the relationship between the record of pension payment and credit score. So using this result of this analysis in encrypted state, so they can help people to get some more credit score by using this pension payment record. And there are also one of the case study in the PET guidebook is also about the homomorphic encryption. So machine learning on cloud with privacy, which means that the running machine learning training task about the text classification in encrypted state. So the purpose of this task is to running this machine learning task on cloud with privacy ensured. And also I add one more use case, which is the building blocks in SMC. So previously I said that in case of the SMC, secure multi-party computation, the communication cost is quite large. So, but by using the homomorphic encryption as a building blocks in the middle of the secure multi-party computation, we can make some kind of trade-off between this computation cost and the communication cost. So there are various works about this combination of these two kind of technology. So as I said, the first fully homomorphic encryption was proposed by the Gentry, but the first concept was at the 1978 by Rivest. And after that, there are various kinds of schemes over there. And actually, the HLib by the IBM is first homomorphic encryption implementation, which is supported DARPA. And currently, there are various kinds of homomorphic encryption implementation, such as the HLib, SEAL, HAN, TFHE, Latigo, OpenFHE, Concrete. Yeah. And currently, the DARPA is also supporting some project which is called DPRIVE, which is for the hardware acceleration for the homomorphic encryption. And also, the standardization is ongoing. So actually, the homomorphic encryption standardization workshop is running at Seoul in Korea. So now, what is the cost of using homomorphic encryption? So first one is the encrypted data process time. So actually, the process time is highly dependent on the parameter setting of homomorphic encryption. And this parameter is highly depends on what kind of function you want to evaluate. So for example, the simple statistics such as the mean or variance can be computed very fast. So, and also for some complex tasks such as the machine learning or deep learning, actually the many researchers are trying to make homomorphic encryption faster using the hardware. So one of the recent results about the homomorphic encryption with hardware shows that 10,000 times faster than the previous CPU result. So I think this helps to reduce the cost, this part of the cost. And also there is another issue about the encrypted data size. So size of the encrypted data becomes roughly the 10 to 1,000 times larger than before by using the homomorphic encryption. But I just want to say that this is also highly depends on the parameter setting of homomorphic encryption. And so please do not afraid of using homomorphic encryption just because of this. And the another cost or another problem or some bottleneck to use the homomorphic encryption is hard to use without expert. So it's partially true, but there are also this line of works which is called homomorphic encryption compiler. So homomorphic encryption compiler try to make non-homomorphic encryption experts can use homomorphic encryption without knowing about the details about these schemes. So I think the homomorphic encryption compiler related works will help a lot in near future. So this is the end of my presentation, and thanks for listening.
So Mr. Salil Vadan of Harvard University and OpenDP is going to discuss output privacy, specifically differential privacy.
Great, thank you, Jess. Can you all hear me okay and see my screen?
Yes, perfectly.
Okay, great. So I'll be talking about the section on output privacy from the guide, which is focuses on differential privacy. I should say I can't take credit for the wonderful text in the chapter. I'm not an author. So my presentation will not exactly follow the structure, but I think we'll cover the same points that's in the guide. All right, let's see. Next. So differential privacy aims to enable statistical analysis of sensitive data with the kind of privacy protections that doesn't want to compromise individual level information. And whenever you use differential privacy, you need to define what do you mean by an individual? Is it one record in your data set that's corresponding to one person? Is it an institute, a business, or some other group that defines what is an individual in differential privacy? By statistical analysis, this includes publications, statistical publications, as often done by NSOs, like publishing statistical tables. It also includes releasing the parameters of a trained machine learning model, as is commonly done by tech companies, and as Rob mentioned in the intro, can include publishing of synthetic data. And we refer to it as output privacy because it's concerned with what information is leaked by these kinds of outputs that are published, as opposed to leakage. It is not concerned with the leakage during the computation itself. So in most of what I'll be talking about, we're imagining a trusted curator that you trust to hold all the sensitive data and then produce these publications. It also can be used in a query sort of system, an interactive system where analysts get to issue queries that they would like to make on the data set against statistical sorts of queries, running a regression of on variables of their choice, and obtain back protected results that are protected by this differentially private curator. There are a number of examples of such kinds of query interfaces that are already out there, typically not using differential privacy yet, from government agencies, from tech companies, and so on. for making sensitive data available. The motivation for differential privacy, which is discussed in the chapter, is that the traditional approaches to protecting data that is released, the outputs, are known to be often ineffective. If you try to just anonymize data by removing identifying information, the data can often be re-identified. And then even what look like aggregate statistics, aggregate statistical publications are subject to also potentially severe privacy attacks, such as database reconstruction, where an attacker takes all of the published statistics and is able to reconstruct most of the underlying sensitive data, which is then can be subject to re-identification, or membership inference attacks, where from the published statistics and some information about a target individual, an attacker is able to determine whether, with high statistical confidence, whether they're in the sensitive data or not. And so these sorts of threats and realization that our traditional methods for protecting against kind of such attacks are ineffective are what motivated the introduction of differential privacy. Right? So we've talked about what differential privacy aims to enable in terms of utility. Statistical analysis, all right, so not the kinds of analyses where you're trying to pull out information about specific individuals, but rather learning about a population. And then you want to protect individual level data, and differential privacy demands doing that in a very strong way, regardless of what attack strategy an attacker uses, what background auxiliary information they have. And the way it's achieved is by injecting small amounts of random noise into statistical computations to obscure the effect of each individual, but still allow signal about the population to come through. This leads to what's a privacy utility trade-off, that the amount of noise you introduce governs the level of privacy protection you have and also the level of accuracy. So more noise means more privacy, but less accurate results. Conversely, less noise means more accurate results, but weaker privacy protections. This is a feature that's exposed by differential privacy. It allows you to make informed choices about where to be on this privacy utility trade-off. But it's not because of differential privacy that this trade-off exists. This trade-off exists inherently because of the kinds of attacks we were talking about earlier. And this also leads to this, typically this level of privacy protection is governed by a private, and the amount of noise governed by a privacy loss parameter. It's often denoted by a Greek letter epsilon, the privacy loss parameter. And when you do multiple releases with differential privacy, there are composition theorems that say how the privacy loss degrades as you do more statistical releases. And so this leads to the concept of a privacy budget. And one of the challenges, the costs of using differential privacy, is making the difficult decisions about how do you set your overall privacy budget, how much privacy loss are you willing to tolerate on your data subjects, and then how do you partition it among the various uses of the data and statistics you may want to support. And as well as tolerating the loss in accuracy you get from enforcing this privacy budget on your releases. So just to contrast with, I guess, mainly the middle bullet here. So differential privacy, again, is ensuring that the outputs of the analysis don't reveal individual level information. The other technologies, like we just heard about, secure multi-party computation, homomorphic encryption, as well, and trusted execution environments, are concerned with preventing leakage during the computation. And their point is also to handle the case where you don't necessarily trust one party to hold all the sensitive input data. Differential privacy can be combined with those input privacy techniques. And there are also a couple of sort of standard models of variants of the model of differential privacy that kind of are a blend of differential privacy and some of these kind of input privacy. So we've talked about the central or curator or global model of differential privacy, a trusted curator who handles all the sensitive data and then protects the releases that are made available to analysts. There's also the local model of differential privacy, which has been implemented by some of the tech companies, where differential privacy is applied on the individual data elements, before they are sent to a server or aggregator that computes the statistical results, provides a stronger level of privacy protection, but has the cost of generally significantly higher levels of noise. And then there's intermediate models, which you can think of as using differential privacy in a federated sort of context. There's lots of literature on what the kinds of statistical analyses you can do with differential privacy. Pretty much everything you want to do in terms of statistical analysis, at least in principle, in theory, is compatible. And there have been a number of, lost my mouse, apologies. See if I can get it back. Okay. Exciting deployments of differential privacy. The largest scales by the U.S. Census Bureau for the 2020 decennial census, the public use products. We mentioned some of the uses of differential privacy by tech companies, which started with the local model by Apple and Google, but now are also using centralized model forms of differential privacy. The tech companies used differential privacy during the pandemic to make mobility data available for policymakers and epidemiologists. And there's a number of open source differential privacy tools available that are listed in the chapter, one of which I'm involved with, the OpenDP open source project. And so let me just conclude by encouraging all of you to join the OpenDP community. It's really a community effort for building trustworthy differential privacy tools. And you can just look us up and find our Slack and mailing list and GitHub. Thank you.
Thank you so much. And let's see if we can have the presentation on trusted execution environments.
Okay, so I'll talk about trusted execution environments. So like maybe just a second slide. I can't see the slides. I'm speaking to without seeing the slides. So I'll talk about trusted execution environments, and like homomorphic encryption and SMPC. Basically, TEEs enable input privacy, but they also provide code assurance, right? So they protect the input, but also guarantee the codes or the computation that is being run on the data. TEs are sometimes interchangeably called secure enclaves or confidential computing, as this is what they enable. 3 different terms, but essentially more or less the same thing. However, even though they're also about protecting the inputs, the security model is very different from FHE, fully homomorphic encryption, or SMPC. So typically they're based on hardware assumptions, so specific kind of chip isolation, or on the cloud provider offering sort of third-party sandbox. And they really started gain traction with Intel SGX, a chip that was launched in 2015. It had very limited memory, so just 128 megabytes at the time. But since then, a range of new chips and solutions have appeared from ARM, AMD, NVIDIA is launching the GPU-based enclaves later this year, and so on. So maybe next slide. So what are really enclaves? So they're essentially a normal server, but with a few special properties. Next slide. Firstly, they have very limited input and output. So they're strongly isolated from the rest of your computing environment. So this can be invoked by physical separation, but also a combination of kind of hardware and software solutions. So sometimes it might be actually a separate piece of silicon with a dedicated on-chip memory and preventing other processes on the CPU to access that memory that is used by TEs. So that's the case, for example, with Intel SGX. But there are also, for example, so-called hypervisor-based enclaves, such as AWS Nitro, that can be viewed essentially as a sandbox offered by AWS with partitioned memory and dedicated CPUs that doesn't have such strict constraints as hardware-based enclaves in terms of like memory limitation and so on, but it requires trust on the cloud provider. Next slide, please. So the isolation property is combined then with attestation. So attestation process essentially offers guarantees around the code and the environment variable that is run within the enclaves. So it's not enough to know that the data is being processed in that isolated environment in the enclave. You also need to know that it does what it's supposed to be doing. So the attestation document then includes hashes of the executable code, for example, and is also digitally signed. Next slide, please. And using attestation document, one can then establish secure connection with the TEs, allowing to send kind of encrypted packets to the enclave, which are then decrypted for a specific pre-approved purpose kind of computation within the enclave. Next slide, please. So like every pet, TEs of course have their pros and cons, right? So the great thing is that they are a general purpose computing environment. So, you know, it's source code and language and framework agnostics. And in principle, you should be able to just take a Docker container and run it within an enclave. Also, since the data is actually processed in plain text as opposed to FHE and SMPC, there's no computational overhead or communication overhead, like in the case of multi-party computation or computation in terms of homomorphic encryption. So there's a very negligible slowdown. And of course, as mentioned already, the TEs also provide code integrity, which is not necessarily the case with other pets. And another positive thing is that, of course, it's kind of adopted by all major cloud providers now. So you go to AWS, Alibaba, OVH, Google Cloud, Azure, like whatever cloud you have, basically, they will have some sort of confidential computing offering. Now, there are, of course, challenges, and the major one is that you need to trust a physical infrastructure provider or a cloud provider, which of course, it depends kind of what your security model you're aiming at, but it also exposes it to potential kind of side channel attacks as well. Another challenge was that the first generations, in particular of TEs like Intel SGX, were very limited in memory and also only offered CPUs and RAM support. That's going to change. So this year with NVIDIA launching GPU-based enclaves, but there's still kind of limitations as of today. And the enclave model is very much also what is kind of, you know, what you see is what you get. So since an arbitrary code can be run in the TE, the parties that make use of them need to exactly agree on what is acceptable, right? Including the versioning of libraries and frameworks, the sources that they are from, and kind of other security considerations. Next slide, please. As of course enclaves are widely available, they have been deployed in kind of multiple scenarios and production environments. A use case with kind of proof of concept that some listeners here might be very familiar with comes from the UN Pet Lab that used enclaves for trade reconciliation. So as we know, each country records how much they input and export with any other country in the world at also different granularity level. So UN Pet Lab used basically enclaves to pull data, to combine and pull data from different sources, perform analytics, generate actually a PDF report inside the enclave, and share it with the external parties, right? So share with all the parties that participated in the computation in terms of, what might be the major discrepancies in the trade data, what might be, kind of major services and goods and so on. So this also included differentially private statistics, actually using OpenDP library. So of course, the reason for kind of being able to do such a, in principle, like complicated analysis is that is due to the flexibility of enclaves, but it also necessarily then requires kind of bilateral approval of all the parties that then run that code. So with that, I will end, and I'm not sure. I think next is Owen talking about the practical considerations. Thank you.
Yes, thank you so much. And let's welcome Mr. Owen Daniel with the UK Office for National Statistics, who will discuss practical considerations for privacy enhancing technologies.
Thanks, Jess. Hopefully my slides are going to be on screen in a few seconds. So if you can let me know if those are visible.
They are.
Brilliant.
We can see them.
So thank you very much for the invite to speak today. I'm going to present from the perspective of somebody who is working in an NSO to really see if we can start to use privacy enhancing technologies to change the way we go about producing official statistics. And I'm going to present in two parts. I'm going to start by talking about some of the practical considerations when deciding what type of pet to use for a particular topic. And then I'll talk about some of the challenges and mitigations in a more holistic sense. And I won't be able to cover all of the really interesting and great advice that is in the UN guide. So I really encourage people to look at the guide in their own time. but I'll sort of cherry pick the things that I think were most pertinent, at least to me. And the guide makes a really good point about practical considerations, which is that really with any good project management, to put this in a rather banal setting of reducing analysis to project management, but any good project really needs user stories, and having those user stories is a really good way to keep your project sort of delivering appropriately. And I think what the guide does really well is actually pull out what particular user stories you need to take into account when delivering a project that's looking to use privacy enhancing technologies. So I'm going to focus on those aspects today. So sort of thinking how you could sort of specific considerations you want to take into account when working with pets. So the first one is should be fairly obvious, but is always worth sort of being explicit about, which is what are you actually protecting privacy for? So who are you trying to protect privacy for? So that's both whose data, but also which type of user of the data. So from asking that, obviously we can first assess whether pets are genuinely needed or whether they're potentially overkill for the particular setting. But it also drives that clarity of whether we're really needing input privacy or output privacy. And I think it's fair to say that most work in official statistics will at some stage require output privacy controls. But as NSOs or National Statistics Offices move towards more admin and novel data sources, we're going to have increased likelihood of requiring input privacy as well. The second sort of point for consideration is who needs to collaborate. So if large collaboration is required between multiple parties, perhaps from multiple organizations, then some pets are better able to support this than others. So in particular, Enclaves, synthetic data and differential privacy scale quite well with the number of collaborators, whereas other methods potentially don't. And secondly, is there variability in the risk tolerance of different collaborators in the work. So for instance, in the setting of output privacy, where perhaps we're going to use differential privacy, and as Salil introduced, we have this notion of this privacy parameter. Perhaps we have users who we're willing to actually change just how much risk we're willing to take. And so we have varying parameters that we might want to enable for different users of the data. So perhaps for more internal users of the data, you're willing to be more risky than you would with public users of the data. And the third consideration is really what are the technical options and limitations available for the work. So the families of pets that we've already seen introduced today really vary in terms of whether they depend on software. So for instance, homomorphic encryption, secure multi-party computation and differential privacy, or whether they rely heavily on hardware solutions. And I think it's fair to say that working within a government agency, both of these, which is easier to actually implement, is really quite varying. So government agencies, at least from my experience, are often not particularly fast moving. So investing in new hardware can be sort of take years to agree new platforms. But likewise, while software might seem like the more appealing option, quite often there are quite heavy, stringent restrictions on the way that various softwares can be introduced into organizations. And so green lighting a particular piece of software can be arguably just as time consuming, even if it doesn't require the same sort of resource. And secondly, obviously, the technical options are going to be bound by the cost implementation implications of them. And so, for instance, various pets really vary in terms of the extent to which the market size impacts things. So the first two I mentioned there, homomorphic encryption and secure multi-party computation, the market is quite small. So there aren't very many options to actually look at implementations there, whereas DP is fairly cheap to implement because it's widely available. And if you're very risky, then you can implement it yourself. And I'd like to talk a bit about some of the consequences that pets might have on outputs. And I think this is a really important aspect to think about when choosing your pet. And I've highlighted 4 there. So the first is around quality trade-offs. So, for instance, when using differential privacy, we add noise to the data. And as Salil introduced, there's a trade-off there between the amount of noise you add and the utility of the resulting data. And so we really have to decide the extent to which pets might actually have negative consequences on the accuracy of statistics we're producing. Likewise, a similar example might be in data linking, where perhaps using secure data linking methods actually require lower match rates, and so therefore knock-on consequences of those compared to more traditional data linking methods that organizations might use. And in the case of my own organization, the Office for National Statistics, the current advice is to always link in the clear where possible. So not making that trade-off unless it's deemed essential. The second is in terms of the interpretability of some of the pets. So again, in particular, in the case of differential privacy, whether end users of the data can still understand the data and what limitations there are when we've added noise, and how they can factor that into their downstream analysis. We also have to consider the interaction between some of these pets, in particular output privacy, with other outputs. So in my own case, in the ONS, we're currently looking at creating private synthetic data, but there are already outputs from the real data, derived statistics in the public domain. And so understanding the impacts of parallel releases and whether that has any negative consequences needs to be factored in. And then finally, bias and fairness. So as we move towards using more machine learning and AI techniques in the production of official statistics, obviously we'll need to consider more sort of the wider questions about bias and fairness in AI. And when working with privacy enhancing technologies, it can be harder to hold the same level of accountability towards bias and fairness if analysts have to interact with data in a less hands-on way. Finally, I'll touch on some challenges and mitigations from a high level. So one of the challenges for the adoptions of pets, at least from the organisation I'm in, is that quite often the perspective is that the current status quo is viable. And so that's really getting at the, if it's not broken, why would you fix it? Secondly, there's a high level of institutional dependency. So I come from the analytical community, but there's also technical dependencies, legal dependencies, and data owners. And so for us to really move on the adoption of pets, it needs to be a whole organizational buy-in. And it's very hard to drive from a single part of the organization without that consensus that pets are required. And then finally, sort of the overall cost of pets, as mentioned in the point above, as soon as you've got so many different players involved, it's obviously going to be costly purely from a human resourcing perspective, let alone a platforming perspective. And we fall into sort of a first mover problem where almost surely quite a lot of the early use cases for pets, we could probably, not all of them I should say, but some of them, we could probably move faster if we stick with the status quo and just do things the way we've done. But that's not scalable in the long term. But it does make it harder to really pick up on these early adopter use cases. Finally, some mitigations to those challenges. So I think as we move to having more standards for pets, that will raise institutional trust in them. And so I think there's a lot of groups that are advocating for wider standards. And so we're making progress there. Secondly, I think focusing on partnership enhancement is important. And in particular, rather than thinking about how we can refactor existing production of statistics to use pets, we should be looking at the opportunities to produce new statistics that wouldn't be possible without them. And that really does get around that issue of the status quo, because we're basically focusing on the fact that these can enable new partnerships and new statistics rather than improving the old. And then finally, I think it's really important that we should share success stories within the community. And that's really at the heart of the UN Pet Lab and the UN Pet Guides case studies, where the more we can share how these have been impactful and benefited particular communities, the more we'll see them rolled out more widely. Thank you very much. I'll hand back over to Jess.
Thank you so much. At this point, I'd like to introduce Mr. Kurt Roloff from Duality Technologies, who has been invited to share some specific comments on this chapter of the UN Guide on Privacy Enhancing Technologies.
Sure, thank you very much. I'm Kurt Roloff, CTO and co-founder of Duality Technologies, a startup that's focused on commercializing homomorphic encryption technology and privacy technology for commercialization. I'm also one of the main people behind the OpenFHE open source library and the homomorphicencryption.org standards community. So let me share some slides. Do I have the ability? Oh, here it is. Excuse me.
Yes, we see those now.
Okay, thank you. So to line up with what was communicated before, we do see a lot of value in the use and adoption of privacy technologies, not just homomorphic encryption, but TEs, MPC, differential privacy, and so forth, as a way of enabling collaboration analytics on very sensitive data, while also maintaining privacy, security, regulation, and business secrets, and so forth. I wanted to add a few comments specifically about the homomorphic encryption chapter of the PETS guide. I believe that there are some things in there that should be highlighted, and some things that need a little bit of editing work for what it is. First off, to line up and put a little bit of context in some of the things that were shared in the guide, and this is broadly for PETS, but PETS in general, but homomorphic encryption in particular, we do see the security and adoption of and trust of privacy technologies really being a three-legged stool. Imperatively that the tools should be well known, using certified techniques, gone through the academic peer review. In particular, we only use in FHE homomorphic encryption schemes that have been through peer review in top-level conferences and have been well vetted by the open community for what it is. This is just a specific example for homomorphic encryption, but this also holds for other PETS technologies too. Also related to that, we are big proponents of only using open source implementations of the core privacy technologies. I know there's some work that was presented and referenced earlier today about open source. I am one of the main people behind the OpenFHE library, and there's a few core parts of this that we specifically push related to best practices about traceability of where source code comes from, making sure that source code comes from known sources in a large library like this, and providing openness about where contributions came from, including change logs as they are. Then also, of course, very important is the adoption of general security standards, specifically open vetted security standards that have also gone through a similar peer review process. As was referenced from my colleague at Samsung, that we're currently, both of us in Seoul, Korea, at the homomorphic encryption standards meeting, which is also being adopted by ISO and several others. And so we would only, in my recommendation, only use PETS technologies that have conformed with some international standards process, particularly around parameter settings as they are. An example of this that I of course am supportive of is the OpenFHE open source library. As a specific comment about the FHE section of this chapter, a number of the material related to FHE was fairly dated from several years ago. There has been quite a bit of movement in the community over the past 5 or so years. One of which is, of course, the use and adoption of OpenFHE as a broadly used library for what it is. But there is also some comments that in the report, beyond some typos that I shared in kind of more pedantic wording changes, there was quite a bit of discussion about an NCPA attack, which has been completely mitigated and is basically a non-issue right now. It's been mitigated for several years with improvements specifically to the CKKS scheme and several others. And so I don't believe it's necessarily the right message for this to be given so much visibility in the UN report most because it is a non-issue, and could potentially deter the valid use of these technologies for specifically valid use cases where homomorphic encryption has quite a bit of value. I also believe that some of the discussion about the use of the privacy technology usability would need a little bit of refinement. A number of the major libraries do have high-level Python wrappers for high-level usage. Even Google has provided a high-level transpiler to move workloads over to privacy technologies such as FHE. And there's been quite a bit of work that Google's been pushing out in this space too, that is counter to some of the statements in that chapter. And so I would like to request several of these updates to be made, given that there has been quite a bit of progress in the past few years that are beyond what has been listed in the FHE section of the EON PET guide also. And I'm very happy to work with the editors and authors to make these corrections in an expedient manner. So thank you very much. I'll pause there if there's any other feedback, but I'm happy to share my thoughts, and thank you.
Thank you so much. We now have some time for questions, and you will also please visit the website to connect with us regarding any additional questions after this event. But we will now take questions from those attending. You can either put your questions in the chat, or you can raise your hand and be unmuted so that you can ask your question aloud. So I see that there is a question from ESS. So I'll invite you to either unmute yourself or be unmuted so that you can ask your question.
Okay, thank you very much for this very interesting presentation that we have this afternoon. Very quickly, 3 points, 3 questions. One is how if the methodology that has been described today, the PET technologies, different technologies, would be useful for micro data? Is it for the micro data? I mean, the data that's the unit level data, and then how does this PET methodologies go along what we used to call data disclosure methods like anonymization and so forth? Are they really comparable, or are we really talking something new in terms of keeping confidentiality for microdata? I'm specifically asking for the microdata. The second point is one of the important issue of like opening up or sharing of data is to improve research and improve the policy making through sharing of microdata and data in general. So when we apply different PET technologies, how do we see the interoperability? Because the linkages are very important to do some new researches using data that's coming from different sources. So are we really thinking of some standardization, or how do we deal with this interoperability at the end of the day when different methodologies are applied? The third and final point is, I'm looking this third question in regard to the developing countries. When I see the capacity and the resource that's required to apply such a technology, PET technology, I mean, how do you see the applicability and affordability in terms of capacity and cost in developing countries? Thank you very much.
Is there a particular speaker that you would like to address that, or was that a question open to the entire panel?
To the entire panel, I think most of it is connected.
Thank you.
I can try chiming in on the first question, and then maybe the other panelists want to weigh in on some of the others. So thank you. Those are really important questions. The first question was about what is this? Is this compatible with microdata? And the answer is part of what led to the development and introduction of differential privacy was the realization that publishing of microdata is often much less safe than we thought. And even with often very aggressive de-identification of microdata, it's often possible to re-identify individuals. And so really differential privacy is a change from microdata publishing, and it fits more in the tradition of statistical disclosure control of the kinds of methods that were used that are used for publishing statistical tables. It provides a more sort of rigorous methodology for reasoning about the kinds of protections that you get when publishing statistical aggregates. And the closest thing that's compatible to that's similar in terms of end uses to microdata that's compatible with differential privacy is synthetic data publishing. So which something that looks like microdata but is not obtained by just de-identifying individual data records. I'll just touch briefly on the last point from a computational infrastructure, resources point of view. Differential privacy is not so heavyweight. It doesn't require extremely expensive compute resources, but at the moment there's still a ways to go for the open source tools to be usable enough by organizations that don't have a lot of expertise. And we're, the community is making progress on that, but there's still some ways to go. But we hope that it will reach a point where, even organizations that don't have prior experience with differential privacy are able to make use of these kinds of tools.
I'll also come in briefly on the third point as well. In my role, I also cover working in the ONS on with partners in developing countries, and specifically we are actually already looking at using privacy enhancing technologies to enable those collaborations. So as Salil just mentioned, using synthetic data so that we can actually collaborate more effectively. I think in terms of the cost, Salil's already made the point that some of the PETs can be very cost effective, such as differential privacy. I think the other context that one has to see this in is whether PETs facilitate moving to new ways of working. So, for instance, if we consider the cost of running a census can be incredibly costly, but if one could move more of census production, for instance, to be done from administrative statistics, then that might be a cost saving. And so if PETs can facilitate moving to new ways of working, then potentially there are ways to recapture the costs from basically moving where money is being spent to facilitate that work.
I just wanted to comment on the last point from the perspective of the trusted execution environments. So in particular, when it comes to the kind of the costs, right? So the question of that very much depends, right? So you can have, if you need to buy specific hardware, like want to have the chips on-prem, then of course the costs are skyrocket and it's not so straightforward. However, on the other side, a lot of cloud providers try to offer confidential computing, for example, at the very same cost as any other server, right? So, for example, AWS Nitro Enclaves would have the same kind of enclave enabled would have the same price as non-enclave enabled, and same with other clouds. So that's in a sense helpful. As Salil already mentioned, with differential privacy, there's really no additional cost. But with all those privacy and SIG technologies, there's of course like other costs associated, and in particular, costs are associated with training and kind of the higher kind of barrier of entry of changing the workflow, because like how those technologies actually fit into a typical kind of data pipeline, into typical toolings that people use, and lowering that barrier of entry and integrating with the tooling is really kind of where often the majority of the cost would come from, not necessarily only the infrastructure costs. Thank you.
We have a question from Ricardo at INESENUI. Please go ahead and unmute yourself and ask your question.
Hi, do you hear me?
Yes, we do.
Okay, thank you all, especially the speakers and organizer of this highly valuable event. And I have a question for Professor Badhan. And you said this early about what's the state of the art of OpenDP Commons for an application in a, for example, government agency. I'm thinking concretely in a census release in the short term, 3 million, 4 million people approximate. And does it have the capacity for processing and generate some calculation with that amount? And with thinking in local data servers, because I think we can't use a Dataverse, for example, for legal reasons. And other question, bringing back the comments of the presenter of duality, and does it adhere to a standard, to an international standard of quality and for data management?
Great, thank you for the questions. So OpenDP is an open source project, kind of still sort of in development with the community. There is a library that has been released and can be used, but to use it in a production system at the scale that you're talking about requires really the organization that's using it at this point to to have the experience in the engineering to do the quality assurance and so on, where it is not a plug and play production system yet. And so the kind of thing that you're describing is the sort of thing that would need some resources and collaboration. I encourage you to contact our team if you're interested in exploring that together.
Okay, certainly I will do it. Thank you.
Thank you so much. It looks like there is a question from Madhavan Palan.
Hi. So I was just wondering, do you use watermarking as an encryption method under homomorphic encryption, because it will be a multi-layer thingy? Any interesting chips available, because hardware-wise, that of good technologies available, like in mobile these days they use this multi-core processor where you have multiple chips actually used for encryption and decryption sort of thingy. So any ideas on that line? Thank you.
Is that a question for a specific presenter or a question generally for the panel of speakers?
I'm okay with any number of presenters actually. Thank you.
So I'll take a crack at it if that's okay, related to some of the FHE aspects. So I think some of the first part was garbled for me, and I apologize if I missed some of it. In terms of hardware for some of the solutions, yes, there has been a number of ongoing efforts related to hardware implementations of these various technologies, including even various multiprocessor based approaches where there is kind of a core generic CPU, whether it's Intel, AMD, or RISC-V or any of the other ones, and then kind of an associated co-processor, whether it's on the same processor fabric or kind of something like daughter card connected through PCI Express or something like this, to offload some of the secure computations targeted on I'm aware of FHE, but there's also other kinds of things that do work. None of these are really in production right now. Some of them are on very early prototypes. There have been some designs that look at things like the Zinc chips, which have things that look like an ARM processor on the same fabric as an FPGA, where the FPGA is configured to do the privacy protected processing such as FHE. I'm more than happy to follow up offline. This is a fascinating area of research, but it really is more of a research area about these kinds of more exotic processor architectures.
Thank you. It looks like Rob has been able to reconnect.
I have one more. Sorry.
Oh, okay. Yeah, please go ahead.
Sorry, sorry, Jess. So I was just wondering, have we, played with this NSA tool, National Security Agency, actually a tool called Gidra, where you the source is the software is open source, and they have like whole set of tools for program analysis actually. So any thoughts in this particular zone? Thank you. The organization is NSA. Thank you.
I personally, I'll just say because I was the last one to talk, I've not personally used this tool before, but I'll have to look into it. Thank you.
It's available on GitHub.
Thank you. It seems like it's something that we'll be looking into, and we appreciate that you have raised it. So it looks like Rob has reconnected. So Rob, if you'd like to unmute and ask your question directly.
Can you hear me okay?
Yes, we can.
Okay, excellent. Sorry, I've had no end of trouble as whoever is admitting me is letting me know. Yeah. Anyway, first off, congratulations on the second edition and all of this great material. I think it's fantastic. I was part of the first one. My question, I guess, is a little bit looking at the organizational context within which this has to be applied. So inevitably, there are the prosaic aspects of getting cyber authorization and policy alignment and so on within a given organization, or in the case of multi-party, obviously, with all of the various contributing parties. So has there been some thinking about, it's one thing to have the technique, it's one thing to have the skills, it's one thing to have the open source software, it's a thing to basically put together the solutions. But sooner or later, you rub up against some sort of authority to operate type process within an enterprise, where you actually have to demonstrate that not only is the technology appropriate and it's operating as appropriate, but I'm thinking here of things like the NIST 800 controls, that basically you have a concept of operations and a means of operationalizing this, because in the end, it's going to come down to the trust of the contributing parties on the data side, whether that's individuals or corporations. So I love the use case examples, but I do think that one of the other obstacles to adoption and use is how you enable a combination of either the data scientists and the technology people or whoever in any given organization, how you enable their ability to put a solution in place and satisfy the overall commitment on behalf of the organization in terms of privacy, security, and all these other things.
Thanks, Rob.
Does that make sense?
Yes, that's an excellent point. I wonder if maybe Owen might be able to speak to that, or if any of the other speakers would like to respond.
I'm happy to come in, but only to say that I agree wholeheartedly that it's a really important point, and one certainly that we haven't cracked yet in the ONS. And I think this was a really good articulation of I guess what I was trying to say in my slides, of it really needs to be a cross-organizational sort of approach to solving this problem. It doesn't really help if it's just a bunch of analysts who are thinking about this and not thinking about it holistically, but we're still working on it. But I think perhaps there are other organizations. I mean, Matthias, I don't know if you want to come in, because I think that maybe you've got some good examples of how this has worked for you that you've shared before. But no pressure for Matthias to to be able to respond.
Go, Matthias.
Yeah, first of all, nice to see you, Rob, or hear you. and a very good point. I agree with all others that this is an important point. So yeah, there are some ways forward, but it's not easy. So one thing that is happening is they are in the project that worked very closely to the UN task team, the UNECE Input Privacy Project. There was exploration of possibility what would be needed for a sort of private computation as a service where we could have maybe combination of trusted organizations running private computation with some state-of-the-art techniques and provide this trust, but also expertise, which is often a problem in national statistical offices. So that's one direction, and I am aware that in Europe, European, Eurostat is probably also looking into this area as a kind of providing maybe a shared service approach. But there are a lot of aspects of this, so I will not say that we cracked it. Of course not.
Yeah, I mean, I think just as a suggestion, one, I've always been a fan of the European interoperability framework, and it actually talks about the political, the organizational, somewhere at the bottom is the technological standardization, above that is semantic. But I think that when it comes to the practical application of solving a problem and unlocking the power of data, the technology is an important piece. But I think that, obviously there's a social trust, social license to operate aspect to these things, or a commercial trust. And you have to basically contextualize what it is you're putting in place. So the readiness to deploy and operate, I think you folks have touched on some really important things, and I think there's been some clarifications on things like AG, but you still, at the end of the day, there's going to be an executive in charge of an organization who is going to have to accept, he or she, the residual risk that is applying here, and also the guarantee, if you like, that it will be operated properly. And I think that that's something that's often thought about later. And you can design it in and you can start to use it, but if you can't get across that hurdle, I've seen that based on my time at StatCan, as a huge hurdle to adoption, to actually get into so-called production use. So others have tackled this and they've solved that problem, so clearly it can be done. And as I say, there's just some intersection. I use the NIST stuff, for example, the 800 as a guidelines, and so I'd suggest that maybe a little bit of future thinking might have a look at that stuff as well. Thanks.
Yeah, I agree. And since you mentioned the European interoperability framework, there is also another, another development in Europe, particularly about the data spaces concept, where you come with the, security by design, networking approach for certain sectors that also then put some focus on interoperability requirements and etc. So there are ways forward, but we are not there yet.
Yeah, cool. Great stuff. This is fantastic to see it evolve. I'm really impressed.
Well, thank you so much. And my sense is that we could ask a lot of really good questions and have much more great discussion, but unfortunately we've reached our time. And so I just want to thank you all so much for joining today. And I hope that you found the information useful, that you'll share the information that you found most relevant from our discussion with your colleagues. And also please visit our website, where we'll continue to share resources that we hope will be useful for your efforts to advance the use of pets for official statistics.